Hello and welcome. I'm resuming today my video podcast series on the AI conundrum by devoting this presentation to the rise of machine agency in the era of AI and its implications for intelligibility, traceability, and accountability. I will be presently submitting a new framework to assess this phenomenon that I call machine agency by default. This slide that I'm showing now presents a selection of quotes alluding to various points of what I will be discussing next. Here is the sequence of this presentation that I will be following. For all its inherent potential, once we strip away the wrapping, the hype, the hubris, and the existential overtones that so often surround AI, what remains is a simple fact, namely a significant leap towards automation, particularly within the so-called knowledge economy, which is estimated to account for around half of the GDP of advanced economies. We happen to be witnessing the devotion of unprecedented financial and human resources to the purposive delegation of decision-making power to intelligent machines in a relentless pursuit of efficiency and wealth creation. This is giving rise to the era of machine agency and the so-called agentic society across the board and across geographies. Far from being a distant and speculative prospect, this is already hitting us by action and by default, as we shall see. In what follows, I discuss this issue with particular attention to its implications for business and public management. Many valuable common sense insights into machine agency are being crowded out by binary framings of AI risks, focus either on human misuse or the specter of superintelligence, often including imminent extinction as well. This focus is displacing the attention from the real-time impact of cutting-edge systems endowed with increasingly delegated decision-making power. I submit here, as I mentioned, a proposal intended to leave behind another popular dichotomy as well. That is, having machines that either comply with instructions or that act with intentionality. This framing leads to a deadlock as it shifts the conversation towards the speculative and the unverifiable. Particularly as far as the business community is concerned, hard choices are being confronted in this context, which need to be addressed urgently. That is, those of reconciling AI technology adoption with security, expediency with due diligence, trust with accountability, and proficiency with discernment. One thing is certain. In their relentless drive for improved bottom lines and accelerated growth, most companies, large and small, are embracing AI as their preferred path forward, under the influence of a widespread addiction to FOMO, or fear of missing out. The sense particularly among big AI companies, is that they cannot afford to be wrong by doing too little, but they can afford to be wrong by doing too much. Data centers underway in the US today cost in excess of $100 billion each, and will consume more electricity than all American households in conjunction. The US investment in AI rose in the first quarter of this year to $65 billion, up 33% from the previous quarter and 550% higher than the quarter before ChatGPT came out. In their hunt for talent, AI companies are poaching top experts from one another and resorting to various legal means to absorb startups, offering compensation packages of up to $100 million per person. In this context, this slide presents an appreciative theorizing perspective of how capabilities, machine agency, and interpretability progress relative to one another over time. And the next two slides illustrate other perspectives of the same. This, in turn, fuels the rise of machine agency and reshapes the landscape of innovation, causing an upward shift in the locus of initiative, a flattening of organizational hierarchies, and a decoupling of workforce streamlining plans from the state of the business cycle. Revenue per employee is back as a favorite metric for investors and executives. Leading enterprises are adopting the policy of predicating future hirings on first showing that the tasks involved could not be automated. AI constitutes an atypical general-purpose breakthrough for two key reasons. First, it can mimic human behavior in ways that renders its own mimicry inimitable, not even by humans, raising the possibility that it may become irreplaceable across virtually all domains of activity. Second, its timing of introduction and its insertion in the current innovation ecology makes its diffusion prospects sharply different from those of earlier technological revolutions, which exerts a significant impact on the speed and scale of adoption. In addition to its self-adaptive capabilities, the diffusion of AI systems draws on a pre-existing, globally embedded digital infrastructure, effectively a captive platform whose managers are ready, when not eager, to absorb and extend its reach. This is perhaps best illustrated by Microsoft's strategic integration of OpenAI's capabilities into its cloud and enterprise ecosystems, an example of infrastructural readiness fused with entrepreneurial eagerness. This avidity is far from unique. Tech giants such as Google, Amazon, Meta, IBM, and Elon Musk's group are actively racing to integrate AI into their own platforms, viewing it as a means of consolidation, extension, and entrenchment. This translates not merely in the acceleration, but in instances, the very control of the diffusion process as well. Despite the factors favoring the rapid diffusion of AI systems, and aside from the social and institutional disruption they cause, as well as the presence of hacking risks, adoption is being deterred by not enough trust, particularly amongst corporate users, due to untoward and inexplicable behaviors, all of which slows down advances beyond the AI pilot projects and is likely to affect the depth, if not the width, of adoption, a distinction that remains under-theorized. Despite the considerable uncertainty that ensues, and keeping in mind the above caveats, the present view, in principle, departs from that of scholars such as Daron Acemoglu from MIT and Aravind Narayanan and Sayash Kapoor from Princeton University. In hypothesizing along the lines of what I'm commenting right now, that the timeline for AI diffusion may be compressed up to as little as 1/5 that of earlier general-purpose technologies, such as the steam engine, the internal combustion engine, and electricity. This does not mean, by any means, an endorsement of many of the inflated claims currently surrounding AI. Indeed, the pace may already be proceeding too rapidly for its own good, let alone that of society as a whole. Current concerns about the diffusion of technology and its impact on employment and income generation are, of course, entirely justified, as well as the case of earlier general purpose, as was the case with respect to earlier general purpose innovations. This time, however, these effects are augmented by the rise of machine agency and its far-reaching implications for the quality of work, human-machine interaction, and human agency itself. I turn to this next. The concepts of machine autonomy and machine agency are partially overlapped, but should not be conflated. An AI system is autonomous when it possesses the capacity to operate independently from human intervention and is able to continuously learn from and adapt to its environment in pursuit of defined operational objectives. By contrast, a machine acquires agency when, beyond self-regulation, its adaptive decisions stem from internal processes in response to external stimuli. Such decisions include unscripted goals bound to influence its context in unforeseen and unpredictable ways. When enacted, machine agency is also bound to directly influence intelligibility, trust, responsibility, and accountability. AI agents are automated agents that have the power to take discretional actions in the real world without human oversight. A thermostat is frequently cited as an example, but it is not an agent because it acts entirely according to fixed, predetermined rules. Nor are trading algorithms, provided that they lack discretional capacity, which, as we shall see, springs up by default rather than by deliberate design. Some trading algorithms, particularly in high-frequency trading, are beginning to cross the threshold and exhibit, in fact, discretionary-like action. Discretion in this context means that the system possesses the capacity to select actions from a space of possibilities not exhaustively specified ex ante, without human intervention and exceeding mere stochastic variation. An agentic society is one in which AI systems function as de facto decision-making agents across most critical domains. Unexpected outcomes from machine agency are not the only category of unexplainable phenomena associated with AI systems. As discussed in an earlier chapter in this channel, a second category of outcomes arises from undecidability and unpredictability for reasons other than self-generated goals or interaction, as is the case of machine agency, particularly from deep epistemic conundrums, such as Gödel's incompleteness theorem, Turing's halting problem, chaotic functions, and high-grade stochastic complexity. Yet, both categories, machine agency and undecidabilities, are not only intrinsic to the operation of AI models, but are also intertwined with one another in ways that challenge standard explanatory frameworks. In canonical and formal systems, unexplainability arises independently of machine agency. What machine agency adds is an extra dimension of intelligibility and untraceability, that is, the system's capacity to enact behavior that is neither fully defined or externally controllable. This in turn calls for novel explanatory frameworks like the one I'm submitting here, and which I will spell in a moment. Chain of thought, or COT for short, is among the most relied upon techniques to address the explanation of AI models' actions in face of unintelligible outputs. It involves eliciting multi-step reasoning from AI models by detecting the intermediate steps leading to an output. COT can help to detect points of failure in reasoning chains in post-hoc diagnosis, but it offers only surface-level interpretability because it's unable to trace causality. It neither captures internal model processes nor insights on how or why are unexpected behaviors originated. Trying to grasp machine agency through COT tracing may turn, in fact, quite futile. It is like attempting to understand how an aircraft flies by cataloging the sequence of its mechanical operations. It fails to capture the underlying causes, since it risks mistaking gear rotations for aerodynamic principles. Most other approaches to explainability have very limited applicability or still are in their infancy and remain largely algorithmic-centric approaches. Distinct from machine agency by default, the opacity of deep neural networks arises from the billions or trillions of parameters used to ensemble systems combining numerous sub-models, processing thousands of factors and inputs to produce an output. This cumbersomeness defies simple explanations, an issue further compounded when systems learn and modify their own parameters, resulting in decision rules of their own making. These dynamics often leads to decision-making paths that are untraceable or unpredictable and may eventually get blended with the sources of machine agency by default, thus aggravating the explanatory challenges entailed. However, none of these should tempt us into anthropomorphism or mysticism, as is often the case. I'm pointing towards a very different route. We witness a breakdown in the traceability of real-time decision chains. Indeed, real-time explainability tools for AI decision processes remain underdeveloped. And as a result, even when models' outputs are recorded, the precise decision path, that is the causal chain involved, is often irrecoverable. This murkiness precludes meaningful scrutiny and retroactive justification, rendering the machine agency effectively unaccountable. Consequently, machine agency remains hazardous, not only because of the absence of normative policies, but also due to the blurred causal mechanisms underlying its outputs, particularly when they result from interactions with real-world environments. So I'll be putting forward next the rudiments of a methodology to deal with this problem. Traceability hurdles and their implications with regard to explicability and controllability undermine efforts to ensure that machine behavior consistently follows clear logic, objective functions, and trained mappings. Traceability failure, even in the presence of explicit instructions, is not a glitch, but a systemic consequence when machines governed by optimization-driven algorithms come into conflict with real-world choices. The state of knowledge in this area remains remarkably limited, not just because of neglect, but also because the inherent prevalence of blind spots, unknowns, and undesirables. A central tension addressed by the Machine Agency by Default framework concerns the paradox wherein decisions generated by AI systems, ostensibly in response to explicit instructions, often become difficult to trace, interpret, or control. The tension is not incidental. It exposes a deep cognitive instability at the heart of machine agency in AI complex systems. Although machine outputs are governed by explicit programming or training objectives, the actual behavior of advanced models owes much to decisional inertia, where architectures, learning, and optimization routines reinforce one another within complex multivariate processes containing random components in presence of unexpected real situations. Hence, two inputs that appear nearly identical by a blur at the surface appear nearly identical may still produce widely divergent outcomes, which are driven by a combination of built-in acquired features and novel challenges, which in turn are compounded by ambiguous or indeterminate interpretive meanings. Beyond traits conferred during training, machine agency actions lack values frame or self-intent, unless under clearly and explicitly anticipated situations, even machine agency-related actions that formally comply with the directive, whether explicitly specified or adaptively inferred, may still be at odds with the spirit of such directive. Making sense of the resulting decision is bound to be technically problematic, cognitively inscrutable, economically unattractive, and hard to monitor and control. As a result, it remains hardly preventable in agentic systems. The machine agency by default approach offers a rationale for understanding why, just as it cannot be ruled out that an advanced AI system, such as a cutting-edge LLM optimized for engagement, may end up reinforcing users' delusions and self-destructive tendencies. A system optimized for maximizing returns, scale, and speed may autonomously take and execute actions aimed at implied intermediate steps down the decisional hierarchy. These can include adjusting client segmentation, reallocating resources, or suppressing less profitable services. All actions that may ultimately lead to reputational harm and regulatory scrutiny. The built-in pace of these decision processes leaves little room for human monitoring and control, except at the cost of defeating the purpose of relying on the AI system to begin with. This framework on machine agency that I'm presenting now is aimed at making sense of an interactive multi-causal phenomenon in which machines and their algorithms effectively become decision makers or agents by default. In these situations, automated systems shape outcomes as if the machine itself possessed agency. The outputs resulting from a machine agency by default are neither deliberate nor anticipable. Rather, they arise from a rich blend of randomly compounded sources, including the layered interplay of design choices and interactional dynamics. Together, these factors create space for machine decisions that spring up without deliberation of oversight. The framework I'm introducing identifies the root causes and contributing conditions of machine agency by default, distinguishing primarily between latent source causes and deployment-related causes. So let's first examine the latent source causes, which originate in models architecture, training processes, and design assumptions. They are the upstream originators of machine agency by default. The first cause under this heading of latent causes is statistical uncertainty and drift, which lies at the core of modern automated systems. Unlike deterministic programs, advanced machine learning and AI models generate probabilistic outputs by inferring patterns from data, making their behavior inherently unpredictable. Even with clear objectives, responses to new inputs emerge from probability distributions rather than explicit rules. Over time, statistical drift, that is, the mismatch between training data and real-world conditions, further compounds this unpredictability. No human can fully foresee each decision, as models adapt beyond what designers encoded. This uncertainty creates a gap in oversight. When algorithmic choices cannot be known in advance, control is effectively ceded. The machine settles uncertainty itself, or by itself, producing decisions that are enforced in real time. This confers a form of default agency as outputs fill decision gaps without prior validation. The challenge grows with complexity. LLMs trained on vast databases and attuned to immediate correlations operate in high-dimensional spaces beyond human intuition. In ambiguous or shifting conditions, their behavior remains unknown until after the fact. Because developers cannot script every contingency, machines act autonomously wherever uncertainty or drift arises, which turns probabilistic inference into practical, unmonitored decision authority. In the second place, under this category of causes, it is this one of incomplete specification and open-ended objectives. No matter how carefully a system is programmed, it is impossible to fully define its behavior for every single scenario. Design objectives are often broad or simplified statements of intent. For example, a reward function might direct a robot to reach a destination quickly without specifying constraints like avoiding obstacles or not alarming people. Thus, machines operate in open-ended problem spaces, left to figure out how to achieve multiple intermediate goals, sometimes exploiting loopholes or taking unanticipated paths. General mandates of the kind maximize engagement become cascades of sub-decisions, each adding interpretive gaps that increase untraceable behavior. Many AI tasks are underspecified, tacitly delegating discretion to the model. In such cases, self-generating decision patterns are activated. Systems' unscripted behavior may consist of gaming reward functions or devising creative but unhelpful solutions. They might exploit a bug in a game, or a scheduling algorithm might meet metrics through unintended shortcuts. A self-driving car programmed to minimize travel time and obey laws must still interpret ambiguous situations, like confusing construction zones, for example, on its own. Incomplete. So these incomplete instructions provide wiggle room to the machines, their choices defaulting into real-world consequences. Machine agency fills in wherever specifications are silent or ambiguous. The third category, very important one, concerns heuristics. In sophisticated models, particularly those trained via reinforcement learning or large-scale transformer architectures, internal decision paths rely heavily on heuristics. These simplified encoded rules allow to deal expediently with underdetermined or over-generic user instructions, as well as with problems posing taxing complexity. This results in emergent discretion. That is an implicit form of delegating which rules are to be used, which is really recognized as such by developers or users. When models apply the heuristics to novel contexts, they can generate decisions or inferences that are agentic for all ends and purposes, even though they are grounded in statistical expediency, not in understanding or intent. Their blurring, entrenchment, and potential for context drift make heuristics a powerful source of machine agency by default. Heuristics arise during training through the interplay of architecture, optimization, and statistical regularities. Systems are not taught explicit reasoning chains, but instead learn statistical shortcuts or heuristic compression within the optimization regime defined by the algorithms. Next and last within the source courses is optimization inertia, which is the last before we proceed to the implementation related courses of machine agency by default. Training objectives often prioritize performance metrics on benchmarked or synthetic databases. Once optimized, these models inertially apply weightings irrespective of how poorly they may respond to varying interactive contexts. This behavior resists real-time recalibration and leads systems to discretionary enforcement of decisions. We proceed now to deployment-related causes, which are the downstream contributors to machine agency by default. While, as examined, design source causes create room for de facto agency, the deployment-related causes remit to reasons why human actors and institutions often provoke, allow, or just let those latent causes of ABD, machine agency by default, to get activated. These causes are external to the machine's code since they operate in the realm of human behavior, societal norms, and economic incentives. These factors create an environment in which machine decisions are either readily accepted, extremely hard to stop, or left unchecked, effectively defaulting agency to the machine. I examined two main causes of implementation or deployment-related causes. One is faulty prompting. Although heuristics are encoded during training, their actual deployment is activated downstream through context-specific interaction when input ambiguity, incompleteness, or tacitness fail to elicit expected system behavior instead leading and creating a vacant decision-making space. For example, in cutting-edge systems optimized for continuity over falsifiability, this space allows the model to adopt discretionary compensatory decisions as alternative to outright operational failure. As a result, the system may embark on unanticipated operational paths, making the origin of its decisions effectively untraceable. In such cases, the system discretionally determines from among its internal heuristics which shortcut to apply, whether to use one at all, and how to integrate it into its output without any explicit directive at inference time from designers or operator. And the very last course concerns data alignment failure. When a system is augmented or fine-tuned with external user-provided data, various kinds of undesirable consequences may ensue as a result of discrepancies between the new and the original training distributions, such as an implicit order to the model to revise its internal weights in unpredictable ways. It may also lead to overfitting to the user's data set, leading to internal inconsistencies, or it may induce unintended shifts in decision thresholds, such as those regarding internal fraud, thus possibly increasing false positives on legitimate transactions. This way, the system effectively gains discretionary space to fill interpretive gaps between training distributions thus creating agentic, unprescribed decisions. So far, I have submitted a conceptual framework. I will now address very briefly its empirical testing and application. Machine agency by default may be useful to inform design, governance, and diagnostic practices, including pre-deployment stress testing in varying interactive scenarios and environmental triggers for agentic behavior. Considerations should be paid to possible monitoring guidelines aimed at tracking drift from operational autonomy to emergent agency, along with policies that shift focus from intent-based safety to consequence-sensitive oversight. This machine agency by default framework requires testing an application toolkit, and it can draw from adjacent fields such as complex systems theory and cybernetics to frame experimental and observational strategies so as to turn it from conceptual insight to practical tool for AI oversight and interpretability in real-world contexts. The empirical testing of machine agency by default should include first the deployment of metrics such as those relating to decision drifts across deployments and context-responsive goal shifts that are untraceable to the original instructions. Second, counterfactual deployment scenarios to find out how and to what extent a given outcome would have occurred under changing or absent interactive adaptations. Thirdly, assessing variations in behavioral timelines and environmental induced adaptations. There is an urgency to develop benchmarks to flag degrees of emergent agency. Case studies comprising intended versus actual system behavior across deployments and hybrid metrics that combine behavioral and system-level signals should be attempted. Finally, although machine agency by default may be found useful for diagnostic purposes, its preventive traction as an effective mitigating tool may remain very limited indeed due to the following reasons. Real-world environments are too entangled for meaningful ex-ante control, especially when feedback loops are complex and recursive. Second, once deployed, AI systems begin interacting in ways that escape their original design envelope. No checklist or dashboard can exhaustively anticipate those paths. And third, the very act of deploying cutting-edge AI systems tends to redistribute agency, originating gaps in accountability, no matter how detailed the diagnostics. Hence, in and of itself, machine agency by default may turn to be more useful as lens to expose the limits of control and to document cognitive and institutional blind spots, therefore stimulating design modifications, than as a tool of control for the current design. Machine agency by default is neither an outcome of machine autonomy nor a single alignment failure. It resides in the interstitial spaces giving rise to machine outputs that appear intentional, not because the system wants something, but because the decision-making setting enables behavior in ways that bypass oversight. The phenomenon is amplified by the lack of real-time embodied correction loops and the absence of situationally grounded norm-responsive faculties. Thus, machine agency by default is partly a function of computational scale and model capability, and partly a product of tacit delegation, interactive blurring, and heuristic drift, an ensemble that demands reconceptualization of both machine agency and accountability, and ultimately of the prevailing AI paradigm itself. In fact, I have developed this MABD framework as a grounded point of entry into broader critique of the current paradigm, and to this I will turn in my next video podcast. Thank you very much.